So remember that in this coding area, there are a number of options here for running different types of code. And what's important is to always check whether what you are doing is actually the thing that you want to be doing. Right? So let's go to PCA. And please, everybody, open this PCA in Python. Let me know once you've opened this. Okay, so just tell me yes once you have gotten to lesson 2 in Python. Okay, please tell me yes once you've gotten here. All right. Great. So here we go through and we read about preparing the data, right? And let's go into the code here. So what we're doing, just quickly reviewing this, is loading a bunch of libraries. As we will read through this, just go ahead and open Try It Yourself and click on Run, because this will take a little bit of time to actually load. These are some major libraries here. Matplotlib and sklearn will take a while to load. So please click on Run, and let's go back and look over here. So we're importing some of these packages, and these packages are going to be useful for many different things, but specifically we're using a package called sklearn, and you can see here that we're going to be scaling and standardizing our data. Remember, we talked about that last time. And we're also going to be doing principal component analysis. So here you can see that we're taking another portion of this sklearn package. We're also going to be plotting things. So matplotlib is going to be useful. And we're going to be dealing with numbers and things like that. So we need to import all of these. Now here we are importing our data set. Now it's a lot like what we did in R up until now, right? We're importing a txt tab delimited file, so we're going to be using a tab separator, and we're removing the header here. Then we're dropping this marking for groups, and then we do our PCA and plot the PCA, right? So let's first figure out, okay, does this actually work? So here, this is going to be loading for a little bit, but let's go ahead and find this file, cell lines 15 genes marked txt. So you can actually get it from here. So you can just save link as. And I'm just gonna put it in my downloads. Okay, and let's open up this file. This file is right here. So when you are in Try It Yourself, it says you can download the dataset from here. Okay, so let me know once you've downloaded the file. Has anyone else gotten to this point? All right. Anyone else? Now, if you want to know where is this process of loading the data, you can go to View, and if you've got your developer tools, you can go and open up the console. And here you can see what it is downloading. See Python initialization complete. It's ready. Then you start downloading some of these packages. And you can see that it's loading pandas, pits, Python, okay, NumPy, scikit-learn, SciPy, matplotlib, parsing, cycler. Okay, so it should be loading all of these here. Okay, Samitha, just checking, have you found the file and downloaded it to your computer? All right, great. Okay, so this, you got to press on run here and wait for it to load. So let's just give it a little bit more time. Okay, once it loads for you, let me know. It is dependent on the speed of your downloads and dependent on how much RAM you have on your computer, but that's why we're going to be using a small file. Okay, we gotta wait just a little longer. How many of you have Python installed and working on your computer? So just Marek, does anyone else? Okay. Okay, for those of you that do need to have it installed, you can actually go to About, I believe. There's a little tutorial there on how to do that. But let me do this really quickly. I'm actually going to go back into here, and I'm going to, oh, sorry, I'll do this. Import packages should be fine. Then we want to load our data. Right, so load the data. Okay, 1 second. And instead we want to put here, oh, well, let's see, it sounds like this is actually almost done. So let's just take this. So I'm just gonna, I just have this other tab that's got everything loaded. And I'm going to put this here. And we're going to do this. Okay, so here I've already run and I have these loaded packages. So once it finishes, you should have all of these packages right here. If you hover over, it tells you what it downloaded, all the dependencies as well. And then you drop here, so when you go to your Finder or wherever you store your data, you just want to drag this right here. And once you drag it, it should appear in here, and make sure that the name here is the same, right? So let's load it. Here. Line 43. Oh, this actually finished. Okay, this finished, right? Okay, this finished. So let me go back here. Sorry about that. I was not wanting to wait for too long. Okay, so here we have our packages. We've run the packages, success running code. let's say, okay, it doesn't see the file, so let me just drop the file here. And then I press run. What happened here? Oh, okay. Cell lines 15 genes marked is because it's a capital M. That's the problem. There we go. Okay. Well, if you haven't completed this exercise, then it wouldn't say completed. I already completed this exercise, so that's why it says completed for me. Okay, did everybody load the file successfully? Sorry for the delay. Okay, and then what I wanted to illustrate with this is if you just properly have the name, right, and the name is M here, you should see your data. And then if you run your PCA, it successfully ran, and we can plot this plot. So please tell me, does this look like the correct principal component analysis that you need to get as a result of this PCA? Okay, so if you think this is correct, say yes, correct. Or if you think it's incorrect, say no, incorrect. No, okay, so why not? Calamari, why is this incorrect? So can someone tell me if this is correct or incorrect? Okay, so yeah, it doesn't say the y-axis, you're right. So it does have an axis label right here, but you're correct, the y-axis doesn't have. So what else is, what are we looking at? What is this PCA supposed to tell us? PCA, okay, not cluster. Okay, so let's say grouping, right? It's supposed to say, it's supposed to show samples, right? Our objects as we're looking for understanding how does principal component analysis separate different types of uh, samples that I have, right? Based on all the genes. So how many samples do we have? How many samples do we have here in this 15 genes marked? Well, let's take a look at this data set. Okay, how do I know how many do I have? I have 15 genes, right? And how many samples? Okay, so, okay, 52 actually, but let's say DF shape. Well, we don't need to do that. We just know that it is 52, right? It says right here, 15 rows times 52 columns. So, right? So we have 52 columns, but if we run this PCA and then we do the plot, how many dots do I have? Yep. So what's the problem? So let's say it did even account for the column with the gene names, right? So, okay, any other ideas? What do you guys think? What happened here? So I have 14 dots, but I have a total of 15 genes and 52 samples. And I'm trying to do PCA of my samples. So what should I do? How do I fix this? Okay, the problem is that it changed the axis. Well, not the axis, right? So I need to, instead of doing, right now, the PCA is being done on my genes, but I already removed one entry there. So instead of doing it for objects, for my samples, it's actually doing it on the genes. Exactly, right. So instead of the sample. So how do I change that? What do I need to do to my frame, data frame, to make the PCA show me samples? So it's not just show me, right? It needs to be principal component of the samples, not of the genes. What do you think I should do to the data frame? Yeah, well, yeah, it's actually not transform, but it's called transpose, right? Transpose. So how do I do that? So I can go in here and first of all, right, I need to transpose my data. So let's do data T, and I am going to do np.transpose. What am I transposing? What should I transpose? df, right? So df. So right. So now I transposed my df. Let's take a look at what is in my df. Okay. So now I have 15 rows, 53 columns, right? And what if I do data T? 53 rows and 15 columns, right? So this looks like a good thing, but I only have 52 samples, right? So now I can actually do this and drop the axis, okay? So I'm going to do data, 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 and here I will do data T. Sorry, so here I actually need to do data T drop. So did I already? Okay, data T, let's not do this. So I do drop group. Oh, okay, so the axis here is not finding an axis, right? So I just need to change this to 0. Let's do that. Okay, there we go. So now I have 52 rows and 15 columns, right? So now I have this data, which is correct, right? So let's, we don't need to do this anymore. Okay, we've run it. Success. All right, now let's run our PCA and let's now, okay. So now it looks more like the correct PCA. All right, so whenever you do this, just keep that in mind. You actually want to do things that make sense, right? And to make sense, you have to evaluate what you're getting from what you're doing, right? And here, let's just do PLT Y label. We'll do PC2. Y-axis 0, because actually axis means either row or column. And so 1 is going to be your row and 0 is going to be your column. So yeah, so it didn't find it before. All right, now we have PC1, PC2. Okay, so what happened here? What is PCA singular value? So let's run this. So what are these? Let's look at well, okay, enough of PCA, right? So we've done PCA. We can do a lot more with this. This is, by the way, your first coordinates, right? So this is just actual X and Y coordinates. Okay. So now, after this, let's do a little bit of review of where we are. Okay, so we did all of our data preparation. We understand how to do that. Then we did supervised last time and unsupervised the day before. So you guys are now familiar with some terminology. You know, we did PCA. Did anyone try random forest and SVM? Okay, great. Did you look into what the outputs were? Did it make sense? Did anyone have any questions about trying supervised machine learning and doing it in Python? Did anyone have any questions about that? Okay, so everything was clear, I am assuming. So now let's talk a little bit about model accuracy and validation, right? So, but before we jump into that, let's kind of review what types of methods we've tried and covered so far. So who can tell me what this is? What does this plot show? Yep, and we'll review the code for SVM and random forest today. So what is this showing right here? All right, great. So this is PCA. What is this showing? Okay, great. Hierarchical clustering. What is this showing? Okay, Marek seems to be the only one that knows what that is, but yeah, this could be LDA or stepwise LDA, but this is showing us the linear discriminants for our data, right? And this actually shows us the classification problem of detecting a good boundary for the class, right? So we talked a little bit about unsupervised machine learning, and there are different types of methods that we can talk about, where the objective of that learning is to train an algorithm to tell us something about a group, right? And that group is basically defined by a function, and so we can actually infer from that some characteristics of our groups. And there are a number of different ways to do diversity, perplexity, and different types of variance that are explained by these dimensionality reduction methods. We talked about clustering. Hierarchical clustering is the bottom-up approach, where we talked about how we can organize our data into well-defined groups, but then use this hierarchical representation, here shown as a dendrogram. And by cutting off at a specific height, we were able to identify some defined number of clusters. And also we can use that information to visualize our data in a more intuitive way to really extract some meaningful insights from that. Now here, there is a k-means clustering exercise that you can do for clustering. Did anyone do that exercise? The k-means exercise? So one of the things that you can do from doing the k-means exercise, let me quickly show you. Well, I'll do it here. So if you go back here and do k-means in Python, okay, here you import the data and prepare it. And then sklearn PCA will use for visualization of the results. And what we're trying to do here is use k-means with maximum iterations of 300. You can see that the expected number of clusters is 3. And you then also, you also, oh, sorry. Okay. And then here, we can see that we're going to label the data, right? So we need to extract labels from whatever k-means identifies as a cluster. And we can then map cluster 1, cluster 2, cluster 3, and 4, right? Different colors. And then we can draw PCA and do a scatter plot. So let's quickly do this together. Okay, so I'm going to post this here. Okay, so let's, if none of you really did this exercise, let's just go through the code and see what happens when we try k-means clustering. Okay, please let me know once you've gotten to this link. Okay, anyone else? All right, so here again, you have a link to download your gene expression table. Now, if you download this table, you know, this is the 15 genes, so I can actually, we have this, it's not the marked one, so you can go into our original folder and it should be there. So here's our 15 genes. And we have to replace this right here, right? So this, instead of file.txt, has to be, I don't know why I did that. Okay, has to be like that. Now, what do you think is the problem here? Does anyone know what the problem here is? Or did anyone find the data set? Exactly. So ID not found. Why could that be? Let's take a look at our data set. What do we see here? The problem is that ID is a lowercase I, right? So here we just replace this with I. And let's try this again. Success. Okay, so did everyone load the data? Or maybe let me know once you've loaded the data. All right, excellent. Anyone else? All right. So let's wait until we have 5 people that have loaded the data. Has anyone else? Okay, so have only 2 people that have loaded, waiting for getting to 5 people. So let's see. Is anyone facing issues with anything? Your page is frozen. So was it when you were trying to run this? Error loading. So Smitha, what is the error that you're getting? Smitha, what is the error? Ah, understand the problem. Okay. So Samitha, file does not exist. Remember here it said like file.txt. Did you replace it with the right name and drop the file over here? You have to do both. You have to drop the file and you have to replace the name. Samitha, have you loaded it? Okay. All right, so once you've loaded it, what are we doing? We're actually changing this data is typed to float, and then we are transposing this data final. So let's run that. Okay, success running code. Now we are need to import PCA. So we've imported PCA. And what do? We're actually running PCA on 2 components. And then here we're going to start doing our clustering. Okay, so it's pretty quick. And how many clusters? So let's try different things. So here we have 3 clusters, right? So let's see what 3 clusters look like. So if I do run, and then I want to plot my data. Okay, so here I have 4 clusters, right? And they divide up according to these different groups. Let's try. So, okay, so here we have, let's try number of clusters. So here I have 0, 1, 2, and 3 labels. Let's see, so here I want to into 4 clusters. Let's see, this is supposed to be number of clusters equals right here, right? So I'll do 3. Let's do that. So 0, 1, and 2, right? But I will actually plot legend. See, this is 4, right, for scatter plot. So I think this is fine because I've got the labels are only 3, but here I still have the C4, right? So I'm going to use this cluster 0, 1, 2. Zero, 1, 2. Okay, plot show, plot legend. Let's see. Okay, so 0. So PCA, let's do here. PCA 2D shape. Let's do that. do print. Okay, so right there is what it was, 52 and 2. So that's our PCA 2D shape. Okay, 52, right? So what I want to know is when I am plotting my PCA, plot show, k-means labels, right? So let's do k-means label. Okay, here, call map. Number of clusters. Okay, so let's do k-means labels. K-means labels. Okay, so here are labels, zeros. Okay, so that's right. And here we have the labels. So the question is, why do we still have, okay, here we have 3. Okay, 1, 0. Okay, so here actually you can see there's an issue. 1, 0, 2, 3, right? So let's do 1, 2, 3. And I guess if we don't do this, there we go. There's 3. Even though, you know, it wasn't supposed to happen anyways. So there shouldn't be a 3, right? There's not a 3 here. And, you know, if you go through them, there's not a 3. Why does it still show 4? I think is interesting. Let's try this again. Yeah, okay, so it's 3. Okay, so even if we leave this, it works fine. Okay, so did everybody get this? Let's try to change it now to 5. Okay, so again here, where we have k-means and clusters 5. Okay, so what will happen here? We only have 4, right? But that is actually reasonable because what we need to do is we need to add, first of all, here we have C4 and we have C5, right? And here we will have cluster 5. And here we also need to add another one, right? So this elf, okay, so here we have, if it is 4, then let's make it RGBM. I think there's a C, and let's make it Y. So let's see what happens. So this is going to be 5 clusters. So let's run this again. So here we have column map RGBM 1, 2, 3, 4, 5 is going to be C. Okay, what happened here? So unrecognized marker style. I don't know what other styles are there. Let's say and X. There we go. Okay, C5 is not defined because of this. All right. So did anyone get here? Okay, and this is a problem here. You can see C1, 2, 3, 4, 5, cluster 0. So cluster 0, 1, 2, cluster 3, cluster 4, cluster 3, cluster 4, and cluster 5. Well, actually, here you are doing multiple times, right? So here in the settings, you're doing many, many iterations, okay? And so that's why for this kind of random, I don't know, this actually should not be here, I believe. So I believe this one, right? Let's try and see. Let's save it. And let's run it again. Okay, yeah, the clusters though are going to be different. So let's save this also as a PNG. Okay, so here, see the clusters, their ID is different, but it is a stable prediction. Well, yeah, look at that. This one is here, and this one is here, right? So the separation in these overlap areas is not perfect. And so it does get confused every once in a while. Okay, was everyone able to play around with this and change the parameters to see what happens? Except for Janani, did anyone get it working? Okay. Anyone else, or did anyone have any problems with running this? Those that were trying, Daisy, I saw Adolfo, Samitha, Kalomari. Did you get it working for you? Okay, Kalomari did. What about Daisy and Samitha? Okay, Samitha, let's try to figure out. Can you show me exactly what the errors are? Just copy and paste it in the chat. Each iterations of the k-means clustering. Well, I just saved them as a PNG right here. Okay, so name C4 is not defined. So in here, you have name C4 is not defined. Okay, so let's see. So C1, you see C5. So all of these need to be, so check over here in your lines 16, 14, 12, and 10, and 8, that you've got all of those. Do you have them, Daisy? Okay, so this looks like it's correct. Did Y work for you? So make sure that, instead of Y, just use X here. That works. Okay, so Daisy, that for sure needs to be changed to X. And then we have 0, 1, 2, 3, 4. Okay, so this looks fine. And do you have here C1, C2, C3, C4, C5? Cluster, okay. So let's see. You're saying that you've got an issue here. What about over here? Do you have all of these colors set up here? So let me try exactly your code and we'll see. So if I take this, okay, so actually I'm getting something else. So here, let's see, line argument S, RGBMC. Can you try this? Daisy, can you try that? Let me know if it works. Make sure, I think that there could be an issue. Make sure that your spacing here is correct. Oh, okay, this one was, okay. So now here, what is the error that you got here? Tell me. Okay, C4 is not defined. So tell me exactly what you have in there. Is this what you have? Okay, C1, C2, C3, C4, C5. Let's try that. Well, it works for me. Can you just check? Can you just check here on line number 9? That you have. Okay, yeah. So add another one. Okay, let me know if that works. So did everyone else Um, did everyone else get this working? So just so that I know that we can move on, let me know if you got it working by saying yes. Because what we now want to do is we want to make sure, okay, great. Janani got it. Did anyone else? All right, Jerry. Anyone else? Okay. All right, so remember what we did in PCA was kind of similar to this, but in our final plot, we don't have the colors, right? We just got the dots in the scatter plot, but not the colors. So that is your first assignment for our next final session, is to use what we did here to try to add labels to the PCA scatter plot, okay? So, okay, so does everyone, so what you need to do is instead of here, you have a good example where you are taking the prediction of k-means for a cluster, and then instead of using your k-means labels, we will actually take the labels from the group row where we've got the different types and add those labels to PCA. Okay, and so we'll try to review that next time. Okay, so we understood now how to run both in R and in Python, how to run PCA and clustering. So then we talked about supervised machine learning. And in supervised machine learning, okay, yeah, unfortunately, if you don't have a lot of RAM, maybe that's another issue because it does load it into your browser RAM. So in supervised machine learning, we are looking at labeling the data manually. And let's say with clustering, you can see that clustering can somehow be mistaken sometimes. But in supervised machine learning, we want to assign labels ourselves. And there's a different question that we're asking. The question that we're asking is, can this machine, can this model actually identify specific types that it has learned about in a new type of a data, right? So it's okay that it works on test data, but the main question is, after we have validated that it works on the test data, will it actually work in a real life situation? And so when we get the output, the initial output is we get a prediction for each one of our data points, for each one of our samples. And it provides us with some accuracy based on what we have here in our test and train data, right? But the question is, how do we actually know that it will work on a new data set? How will this model work on a new data set? So we talked a little bit about what the training and the test data sets are and how they are organized, that we have to have a labeled data set, basically. We can prepare this ourselves, or we can actually let the algorithm do it for us. And then we looked at a few different methods. So let's explore how this works for the exercises that we have here. Okay, so here I have a random forest in Python, right? So let's go. There's actually random forest and SVM in this lesson. So please let me know when you get to this lesson 5. Okay, let me know once you have navigated to lesson number 5. All right, one more person. All right, great. So here again, you need to load your packages and make sure that you will see more packages actually loaded in here. And now we have a different data set, which is T1, right? You can actually download it from here. Okay, so make sure that your data set is right there. And I'm just going to drop it here. So here I have my T1. What does T1 have in it? It has IDs and class for all of my samples. So I'm just going to drop this right here and run this code. Okay, so once you have run this, you can check by running the next one that everything is loaded. And then you can check what are the actual names of classes. And you should have 4 classes. Okay, so maybe once you get to here, let me know. Once you get to 1, 2, 3, 4, number 4. Okay. Okay, the important part here is that actually separating, so you can see here, and this is an important part of it, is that we here are separating our data set into 2 portions, right? We're separating into a test size to be 0.4, right? So we're just basically taking 40% of our data. Remember, we talked a little bit about this yesterday. The problem is that we have some groups of samples that are very good, like they have many samples to take from, but some of them actually only have a few, right? So what is going to be 40% of 5? What is that going to be? Right, so the problem is, right, if I have a lot of variation there, how is that going to play out on my training of the model, right? The same thing with the basal ones. I believe there's like only 4 or only 6 of them, right? So again, we're not going to be getting a lot. So, okay, now we have the model, which is the random forest classifier. And here we are trying to fit our model onto, by looking at the training data. We're training the model from the training data, and then we want to predict the outputs from this model onto the test data, right? And so here, your predictions, okay, look at the predictions, right? Let's just save this prediction real quick. Okay, so this is my prediction. Let's change this. Did anything change? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Right? So definitely the numbers change. And if I, because it used to be 30%, now it's 40%, right? So it increased. And the question is whether my predictions are going to be correct, right? So that is another thing that we want to test. So let's look at my, well, let's run this. And here we can print out the classification report, right? So let's run the classification report. Once again, we'll try this once. Okay, so this is our classification report for 40%. Let's go ahead and change it back to 30%. The test data is coming from the same file. So it's actually, separating it into 70 and 30%, right? 70 on the training and 30 on the test size. Does that make sense, Hidia? Hidia, did that answer your question? Okay, so let's take a look at these results. You can see that the numbers are changing, right? So here I have my outputs for each one of my samples. Right? Did anyone get these numbers? Okay. So you can see that these numbers are starting to change. And what it is basically the prediction for each one of our, so basal for, it's basal, cloud, and low, luminal, normal like. So this is like your matrix. You can see that it is making some mistakes, right? So the accuracy is not complete, is not perfect. So let's print out our overall accuracy, right? So the accuracy, if we do 30, is 0.75, right? And here you can see, right? So this is your average prediction for your individual classes. So there's 4 classes. Okay, let's run it again on 0.4. Okay, and so our accuracy increased to 81% as we had changed the proportion of our data, right? So it went from 75% to 81%. Okay, so let's take a look at what will this actually show us in terms of our confusion matrix, right? So if we plot our confusion matrix, what does this mean? So what do you think it means that there's 5 for basal on basal, right? What do you think this actually means, this 5 means? Okay, so Hidia is a little bit lost with the input data. So the input data, look, we are taking the cell lines 52 samples expression data T1. Okay, let's take a look at what does this data actually look like. So if you print out data, okay, it's got almost 7,000 rows and 53 columns, right? Let's go to the top. So here, your first row is your first ID, right? This is going to be your name of your sample, and then your class, which is the different classes. But then instead of using this, we're going to take the features, right? And that's going to be your first row. That's going to be your first column, sorry. And then you also have your values stored for your training, which is all the class data. So your class data are your unique values in Y, right? So here you've got your unique values. And then you take this whole data set and you separate it by, having 60% in your training data and 40% in your test data. Right? So it is an automated procedure to separate, features are your genes, but what it separates, all of your data into 60% of your samples are in your training data, 40% are in your test data. Does that make sense? That how it separates the data into two portions, test and train? All right. So, okay, so we got through how we do the data, and we can see that the accuracy changes every time we do this. So the proportion of our training and test data is important. We actually have to make sure that we have good representation. So let's look again at this plot, and let's think about what it means. So what do you think it means when it's got this number 5 over here? Well, it depends on your data. It depends on how many features, and it depends on variability between your data sets. So within your class, how many, right? We looked at that by looking at clustering, for example, right? So when we looked at the dendrogram for clustering, remember we had an outlier. And in maybe some other groups, basically if your clustering doesn't work good, your classification might also not work very good. If there's some confusion for some of the samples between which class does it belong to or which cluster does it belong to, that means that it's not a very good representative of that class. However, if you have, in real life, these are cell lines. Remember that cell lines have been produced in a lab. They're fed the same thing. They're under the same conditions. Their biology is very similar. They come from the same person. But when we have, right, Janani, right? So 5 right here is that, it was correctly identified 5 times. But it shows you how many do you actually have. So you can see that in the normal like, you only have 3 that you could test for. And here's where your confusion, cloud and low, one time was assigned as a basal and one time was assigned as a cloud and low, even though it's supposed to be 2 over here. And normal like, instead of 3 times normal like, it was 3 times assigned as basal. So that's where the confusion is, because in your test data, you only have a small number of samples for cloud and low and for normal like. Your luminal and your basal are okay. Luminal has 11 and basal has 5. Remember that you have a total of 52, right? So here you have 5, 6, 7, plus 11, that's 18, plus 3, so that is, 21. So 21, right? So 21 divided by 52 is 40%. Okay, so you can see here that having only 2 samples in your cloud and low and only 3 in your normal like was not maybe sufficient data, because normal like completely failed and cloud and low failed half, 50% of the times. Does that make sense? And Daisy, did that answer your question? So let's try to do the 30%. Let's see what happens if we do 30%. Or let's do more. And what if we do, well, let's do 30%, right? So again, basal, it does a pretty good job. So basal, it identifies as basal all the time. Cloud and low, it still has this problem, and normal like it has the same problem. So actually by overall, changing the percentages, we're only changing the number of luminals. We're not actually taking any more. So the other parameter that you have here, random state. Let's try this and see if something changes. You see that your overall changed to 81%. So let's see what happens. Okay, so here we have, okay, so what happened was basal was correct, luminal was correct, normal like was still bad, and cloud and low. Okay, let's try that again. Okay, unfortunately, I don't know, is there? Okay, there we got some different numbers here. Let's see. Well, still 81%. Okay, so the improvement was it only took one of the cloud and low. Okay, so the thing is, right, so here you don't have any control over, it's supposed to make it random, right? So instead of selecting, right now, you can just take everything and just, split it at a certain column and say, okay, this is my training, this is my test. It's supposed to take random ones from your data. But the point of this exercise is to demonstrate the significance of your training data on your outcomes. For example, just because my accuracy increased here, right? I have 81% accuracy. Like the problem is that in my test data, I only had one cloud and low. So it's not just the overall accuracy of the model that is important. What is important here is to also have good representation, balanced representation in your training and in your test data. So if you have a total of 5 cloud and low samples, and 4 of them were in your training data and only 1 of them in your test data, that means that, by chance, maybe it's exactly the same like another one, and it's easy to classify. If you start having more variability in your test data, maybe it will start making mistakes. So ideally, you should have a good representation of your classes in your training data and a good representation of your classes in your test data, so that at least at that stage of model testing accuracy, you can be confident that you are finding good predictions, even though you have some variability in your data. Does that make sense? Okay, the features are genes, but classes are types of samples. So classes are like types of your samples. The features is what characterizes those types. Features is like, okay, if you take an apple, you can say the apple is red, it weighs a certain amount, it's round, it's got a little straw coming up from it, right? Those are characteristics. They're like the features of the apple: color, shape, weight, etc. When we're talking about samples and gene expression, they are genes because genes have levels of expression. So they actually could be used as characteristics of that sample. Okay, so did everyone else go through this exercise and kind of understand what's going on? Okay, can we see? Okay, Jerry. So what is the question? Because we have to get this, I think clarified because the next assignment has to do with preparing your own, working on a different data set. All right, excellent, Adolfo. So, but does the concept of accuracy here make sense? Because the concept of accuracy is very specific to our training and test data, right? That is one of the things that you want to remember. Okay, so Jerry, let me know what the question is. Where is the confusion so we could clarify that? And does anyone else, so far I understand that Janani seems to understand, Marek seems to understand, but maybe a few others are still not clear. Okay, Daisy's got it. Did anyone else have any questions about this? Because we do have 19 people here, so I just want to make sure that, you know, everybody else has good clarity about what we're doing. Does anyone else have any other questions? Okay, so the confusion matrix shows us, you can see that on the y-axis and the x-axis, we have our sample classes, right? These are the types of samples that we have. So if my x and y match, like this is basal and this is basal, that means that I have, this is representation of my test data. Okay, so, right, so Adolfo is correct. So here we have 3 plus 1, that's 4, plus 9, that's 13, plus 3, that's 16. So we have a total of 16 samples in our test data. Because how does it measure accuracy? It says, okay, I trained my model on the training data. Now I'm doing prediction. So I am telling you what I learned on the test samples. The test samples are 3 basal. So out of 3 of basal, it predicted correctly that they are basal, right? That's correct. Because it's got the answers, right? Then for cloud and low, it had 1, and it correctly identified 1. For luminal, it was 9 that it correctly identified as luminant. And for normal like, what did it identify normal like as, Jerry? What did it think normal like was? Yeah, there were 3 of them, but what class? Right, so it thought it was basal, right? So it was normal-like, but it thought it was basal. And that's where the confusion is, right? So that's why it's called confusion matrix. It confused the normal-likes for basal ones. Okay, and if you play around with this a little bit more, just like we did before, you'll see that every time the most issue that it's gonna have is with the least amount of data. Because let's look at our data set again. So this is our data set. How many normal likes do we have? We have 1, 2, 3, 4, 5. That's it. We only have 5 normal like out of 52. So if you do 5, right? If you do 40% out of 5, we said it's 2 and 3, right? So 60% is 3 and 40% is 2. So it means that it only has 3 examples to learn from. If it had more examples to learn from, right? Or if the data set overall, in other words, would be more diverse and more number of samples potentially, it would actually be better. Okay, does that make sense? Okay, so now the other thing that we can do, okay, okay, well, let's finish this and then I'll explain to you the next type of the challenge, so to say, to see that you actually understand. So another way that we can measure this is we can make a ROC curve. So a ROC curve is a curve of prediction. Again, it kind of takes the confusion matrix and it plots us right here. You can see what is it actually doing. For each one of our classes, it will produce a curve. So for example, the red one is normal like, right? And so it identified all the normal likes correctly. For all of the other ones, right, it did it, right, so normal like is actually, so it looks like here, there is a little bit of an issue because we know, let's run this again. Yeah, so the normal like is actually the bad one. How many overall? We had 5, right? And so 3 did not plot correctly. Let's take a look that maybe the labels are incorrect. So we need to calculate, okay, to make a ROC curve, we should binarize our class labels to one-hot vectors. So each class represents a binary vector. For example, first class is 1, 0, 0. Okay, so we have vectors. And then we want to have a prediction quality basically measured for each one of our classes, right? So let's try this again. Okay, so I think here, and I'll take a look at this code, I believe that the labels here are incorrect because it actually should be this purple should be normal like. Okay, so I'll take a look at this, and you also take a look at this, because essentially what it's supposed to show is how many out of the ones that were there were actually accurately predicted. You can see true positive and false positive, right? So if it has a false positive, that means it identified it incorrectly. And so we're supposed to see here if the total area is equal to 1, just like these, right? That means it is 100% accuracy. But if it goes below that point, that means that it has some confusion about it. And so when you have a ROC curve, your basically random prediction is this line right here. So anything above here is some good quality of prediction. And as soon as it goes to 1, it goes to 100% prediction. And that's where some problems begin, right? Essentially, when you have 100% accuracy, it's a good thing because you're getting good prediction, but it's also a bad thing because it means that your model could be overfitted. Overfitting basically means that you are so good at predicting the data types in your test data that if you try to generalize your model, for example, you try to take some completely other data set, like instead of cell lines, you take TCGA data sets and you try to do the prediction, it will be completely off. Your accuracy on validation is going to go down. And that's really what happens a lot of times in real world. So you read about these papers, they train some model, prediction accuracy 90, 98%, really good. Let's try it in real life. In real life, nothing works. Why? Because of overfitting. Because your training data set, your test data set were not prepared very well. So relying on just some of these tools to automatically select the data from you has its benefits and has its downsides. You have to really be thoughtful and mindful of what is it that you're feeding your model. I'll leave this for next time, but let me briefly explain to you the second part of your assignment if you have time to do this. So here we have some data set from the Cancer Genome Atlas. Okay, so let me just briefly explain what this is. Here we have 43 cases. Okay, so let's actually take the 42 cases. Okay, so here you have 42 cases, and I'm going to give you this link here in just a second. My Dropbox seems to be restarting. So I will put this on the forum actually, but I'll just explain what this is. Here you have information about 43 samples. And these 43 samples actually have a specific number of classes. So you will see here that they are coming from patients with different risk factors, different types of stages, different types of ethnic background. So you will have a number of different parameters to choose from. And your objective is to really explore which one of these objectives, or which one of these factors, which one of these categories or classes is most visible in your data set by first exploring the data, and then to train a model to predict on your train and test data with some level of accuracy what these classes are. Now, if you went through all of random forest here, you will see that your random forest actually produces also a list of most informative features. So it doesn't only show you the actual accuracy, it also tells you what are the most informative features. And so we'll talk a little bit more about that in our next session, but try to play around with this data set. So I'll put it on the forum, right? So assignment 2 is going to be take the LIHC TCGA cancer data set, explore the variability using various class/group data for risk, ethnicity, and stage data. And then using random forest, train a model and use the extracted list of features to identify most interesting features for classification. Okay, so that's an assignment. It will take a little bit of playing around with the data, but we don't have that much time left together, so I really wanted to see whether you can apply your understanding of what we're doing here to this idea of finding doing feature selection, essentially is what it is, based on your understanding of classification. Okay, so that's it for today. I will see you all tomorrow morning, and we'll continue talking about classification and kind of how do these models actually, how can they be used in real life. Before we complete today's session, does anyone have any questions about the assignment or about what we did today? All right, great. So again, I'll post this information on the forum, so look out for that. And I'll also ask Beepster to follow up by email to send it over to you. Thank you again for joining today, and I'll see you again tomorrow.